Hey,
Hello. Hi, nice to meet you. Hi, what can I call you? Dr. Jatavallabhula?
Krishna is fine. Yeah,
Krishna's good. All right. Thank you for agreeing to meet with me after so many reschedulings.
no, I'm glad we could connect.
Yeah. Um, yeah, thank you. Thank you so much. So I think this should only be about 20 to 30 minutes, just some quick questions that we had. And
For
then
sure.
do you mind if I record this? Um,
No, go ahead.
okay.
Uh, yeah, I think Zoom tells me it's recording already, so that's fine.
Okay. Awesome. All right. Well, yeah. All right. So, yeah, just a couple quick questions. And then to start, could you tell me a little bit about yourself and like your journey in computer science and robotics?
Yeah, so I'm Krishna. I'm currently a postdoc at MIT, and I do robotics very broadly. Like lots of there's a lot of projects I currently work on, all spanning robotics, computer vision, AI. And yeah, my journey in robotics has largely been I started out as a hobbyist, like always liked robotics as a fun pastime activity, like doing all the Lego Mindstorms, like
Hmm.
uh activities back as an undergrad, building various kinds of robots from all the scrap and junk you could find. Uh so it was largely just from the aspect of like I liked participating in robotics competitions, and that's how uh, initially, during the first year or two of my undergrad, I was doing robotics. But then I started developing a more profound interest after, and then eventually I just wanted to take up research. So that's when I decided to do a master's and eventually a PhD. And yeah, after that, I got this postdoc offer at MIT. So I thought this would be a good place to yeah like learn from some of the more experienced robotics groups out here. Good compliment from where I was, like I did my PhD back in Canada. So yeah, I've been in robotics for, let's say, last 12 years or so, and over the course of those 12 years a lot has changed, and again a lot has also not changed, but we can the most significant changes we've seen are like just how much development there has been in AI in general. Like you have very nice AI technologies of today, and I think a big question in the robotics community is how do we roboticists think about integrating all of that technology into our stacks. So it's very exciting times to be a roboticist.
Mhm. Right. Yeah, I was gonna say, your your introduction to robotics through robotics like competitions is something that a lot of the members of like the group that I run at school is, a lot of the people are part of our robotics team at school. So, that's a cool path that you took there to get from, your work at IIT to MIT now. Um,
Yeah, and that's also true of a lot of my friends. So I can look back to the robotics club equivalent of what we had back during my undergrad, and a lot of those people are still now doing robotics in various different forms. Not all of them just ended up choosing the same academic trajectory that I did.
mhm,
A lot of them go on to work for uh, industry. Like there's people at companies building robots. Yeah,
mhm.
think of the Teslas.
Yeah.
Yeah, these self-driving car companies. And yeah, so I would say a lot of people have robotics competitions as sort of the entry point.
Mhm,
They start out just out of hobby. But there's also other paths that are relatively normal. Like a lot of people might just come in to do a computer science major in undergrad, and then they're interested in research opportunities, and then they come across like a robotics class or a professor doing robotics and then get into robotics research that way.
mhm,
So I've definitely had students who I worked with over the last couple of years uh, who had no formal like exposure to robotics, but they were just interested to explore, and things worked out. Yeah.
mhm. Kind of like having the drive, right? The drive to learn. Do you think that plays a big role in how you get from the general application of computer science to the more specialized field of robotics, I guess.
Yeah, so uh, there's like some specific things in robotics that uh, you don't get in some of the other areas. There's a lot of areas of research in computer science where it's largely about like writing new software
Hmm.
to do things. Like there's no direct connection with the physical world, but when you're doing robotics, you're also thinking about the entire system. So even if you haven't built the robot yourself, you're still having to operate within the limits of whatever the robotic platform might offer. So you might have these. So there's one of my friends who describes their research area as like shoddy robots. So
Hmm.
build robots out of very cheap equipment and electronics, and naturally they're not going to be as capable as you reliable, like the levels of
Yeah.
reliability you expect out of industrial grade robots. You don't get the same out of these like
Hmm.
cheap pieces of plastic and metal. So there's unique challenges there, uh, and yeah. So the thing with robotics is it's not just about software. Like you need your software to work, but it's also about how that connects with the physical world. So
Hmm.
what kinds of motors does your robot even have, and in what ways can it affect the physical world? So if you're thinking of a tiny RC car that moves in a very different way, and that's capable of fundamentally a different set of things compared to something like a quadruped or like a static tabletop.
Hmm.
So
Right.
yeah, all of that goes in, and yeah, to me that's the most exciting aspect, like this integration of various kinds of sensing equipment
Mhm.
to like then the computation that you do, and more we start seeing like a lot of AI creeping into this like sensor and motor interfaces.
Right. Yeah, I definitely see that. Actually, where we live, I think, just about an hour north from MIT, and there's a couple of MIT funded like robotics companies in our area. Like I think one of them is working on autonomous helicopters, and you can like really see like the difference between, I've played around with like Arduino things and like what they're doing on that the completely different level, right?
Great.
Mhm.
Yeah.
Right. So I know you probably touched on it, but is there like any moment or kind of like learning experience that you had that like really was like the spark that ignited like your interest, or was it more like a like a slow process that you got interest in AI and like robotics?
Yeah. So I would say it's largely gradual, but there were
Mhm.
definitely like some uh you can look back at some moments and say, oh yeah, like you've decided at that point, like your interest just gets rejuvenated and you're like motivated to
Mhm.
work further. So one of the earliest moments I could remember was like uh, yeah, back in my first year of undergrad, we were participating in this robot like line follower competition. So there'd be like
Mhm.
uh, a very like skewed and curved path, and you'd place like a robot on that path, and your goal was to like just have the robot trace the path as quickly as you can. And you would have specific constraints on how large the robot can be, how much power it can consume, and all that. So yeah, under those requirements, you're supposed to design a robotic system, like build the robot out, but also like design the algorithm that would uh, enable you like follow faster than the other teams would. So yeah, the first time we actually got our robot to work, like, and uh, in our first attempt, like we did not want to buy anything from like just off the shelf vendors. We also wanted to get that full experience of, well, let's buy everything right up from LEDs, photo resistors, and then let's actually try and build like line
Yeah.
sensors and the entire algorithm. And at the time, we were also using life would have been much easier if we were using Arduinos, but we decided to go like bare metal, and we were using the at mega processors that you would typically find on Arduinos, but without all of the nice Arduino C++ or Python bindings. So we had to do like a lot of assembly programming. So but once the robot started working a few days before the competition, that's when I was like, okay, I can like I have a complete picture of how the robot just senses like just various colors, largely like
Mhm.
black, white, and some whatever shade the line might be in, and that is all like processed into this one decision of how fast should I drive each of these motors.
Mhm.
So yeah, that was very helpful, and I think back then that was the kind of uh, just yeah, it was just that tiny bit of kick you need to
Yeah.
keep
Mhm.
going. But again, like during my masters, I've had these other moments where uh, yeah, I learned about uh, graph optimization and linear algebra and how this
Mhm.
is all tying into like real-time robot perception. So that opened my mind to a lot of new possibilities.
Mhm.
That is more in terms of research. Like I definitely felt like, okay, now with these skill sets, I can actually contribute. So it's not just me building robot systems using what's out there, but just believe that you can now create new knowledge, like advance the understanding of the field. And that's where like I decided I would do research, and robot perception is a theme I could see myself doing research on. And yeah, like every research project you do, there is like at least one very significant moment where you realize that things are really beginning to work,
Mhm.
and uh, yeah, that coming together of things is what keeps driving you one project after the other.
Right. Yeah, actually, I was gonna kind of branch off into that more academic part, and you touched upon graphs and graph optimization. I was looking at some of your previous papers, the recent one about concept graphs, and I was wondering, could you give a simple overview about the work that you did in the concept graphs paper?
For sure, yeah. So the, if you think about broadly like robotics as a field of its own, like any robotic system largely has like three components. There's a like perception, which is largely responsible for taking all of the information, like ingesting the information from the onboard sensors on the robot and converting it into some kind of representation that is fed to all of the modules downstream. So there's perception, which is basically how your self-driving car, for example, you just switch the system on with all its cameras, it senses
Mhm.
where the road is, what else is out there on the road, and traffic signs and everything else. And then there's like the planning module, which is the bridge between, well, you now know what is around you and like where you are, then how do you get to wherever you need to get to?
Mhm.
And that is part of the planning module. And planning can be as simple as just planning like a shortest route on a graph, like think of Google Maps, finding a
Right.
route from school to home. But it can also be much more complex for other kinds of robots. Think of like a full scale humanoid needing to avoid other obstacles in the environment while like trying to uh, maybe carry like a coffee mug
Mhm.
that's filled nearly to the brim like with coffee, and it does not have the spill. So that's much more complicated.
Mhm.
But yeah, that's largely planning. And then there is low level control. So you have a plan to get from A to B, but then what are the motor forces and torques to actually let you get there? So that's part of the control problem. So there's like these three: perception,
Three
planning, and
parts.
control.
Right.
And I am personally very interested in the perception component. Uh, a lot for historical reasons. Like I've been doing research with labs that are really strong in perception, but I also feel like perception needs to be very reliably solved before we can get to planning and control.
Mhm.
And yeah, because of that, I've been looking at robot perception for many years now. And one way that robots build representations of the world around them are via this process called 3D localization and mapping, or usually called SLAM, for simultaneous
Slam.
localization and
Yep.
mapping,
Hmm.
where you are trying to localize yourself in that environment. Like it's just like knowing where the robot is with respect to the world,
Right.
and also building a map of the environment. So it's like what is around the robot question. So this has been like a centerpiece of robotics research for a number of decades right now.
Right.
And
Right.
we have, if you think about all of these, VR headsets that, for example, Apple Vision Pro has a very sophisticated SLAM system running on board, so that you can move wearing that headset and you kind of know where you are positioned with respect to that virtual world. So
Hmm.
it's not just a pure robotics problem. It has lots of applications in adjacent areas like computer vision. Uh, yeah, and also like think of any device you need to be positioned with respect to the real world that has onboard sensing, and SLAM solutions in one form or the other. Like think of smartphones; they have some kind of SLAM or partial SLAM solutions running on board. So that's been one major research area of mine. And over the last 2 or 3 years, like you've seen incredible progress in the rest of the AI community. Think of ChatGPT and all of these other large language models coming in. And now there's like variants of these language models that can process other modalities like images or speech. So that there's like GPT-4 release, which can like take in speech and images as well. So naturally, the question for a lot of people in our community is, how do we like reconcile these differences? There's like traditional localization mapping solutions, but how do they interface with all these new developments we have in vision language? So in the concept graphs work, our idea was to build one such mapping system. Like think of, so the analogy I give to people is, think of Google for the physical world. So you have search engines that are actually able to like sift through the internet for content and like give you uh, the right set of point you to the right set of web pages for a specific query, usually presented in text form. So what would that look like for the physical world, for robots operating in the physical world? Because increasingly I see text or like naturalistic voice interfaces being like the default interfaces for people to interact with AI systems. And this is even true for embodied AI systems like robots. So we built or we redesigned like a mapping system from the ground up, where you move the camera around and you build like this database of objects in your environment. And these objects are not just like uh, pixels or 3D points, but you have language tags associated with each of these objects, so that you can now take your entire representation of the world and have it uh, be queryable via a language model. So
Mm.
instead of just telling your robot like go from A to B, like pick this up to this at this other location, you no longer need to actually write code to perform new tasks. You can rather just ask, like specify these tasks in language. Some of the examples we have on the web page are, I am going to a space themed party. Which object in the scene is the most relevant? And then the robot goes to this. There's a T-shirt in the scene with NASA written on top, and the robot's able to resolve the context and ground that in the 3D scene.
Right.
So yeah, that's where I see robotics, or at least 3D mapping as a field headed to, like more and more sophisticated, but also more naturalistic ways of interfacing with the scene, and tasks get specified in much simpler forms, just like specifying something in language, and robots are able to understand and address these tasks.
Right. And this would really enable the development of more like one robot that can do everything, right? Because right. Um
Okay.
and then
So at
yes.
least the perception level. So there's lots of things that are dependent on the actual hardware. Like does the robot have arms, or is
Mhm.
it just like a wheeled robot without any sort of manipulator on top? So there's definitely like the hardware side of things that still needs more progress, but this is purely looking at it from a perception standpoint. So if a robot is able to create a map of the world with just its onboard cameras, then you get the necessary ingredients to start out. So this would be like a representation that the other systems downstream, like planning and control, can consume.
Right. And then, so what do you, this sounds like a very like multifaceted problem. Lots of different categories that you have to check off to get to the final result. So what do you think some of like the key challenges that you had in enabling the robot systems to perceive these different types of information and, you know, act like a human would, right?
Yeah. So I guess the big learning is it's not a one person job. Like robotics is a big team effort,
Mhm.
and if you look at, for example, the Concept Facts project, there's at least about 15 to 20 researchers
Mhm.
involved in that project, each one responsible for like a different component of the project. And you see that more and more if you go to like robotics companies that are doing like real robot deployment. So like it is really crucial to like have the right team of people with complementary sets of interests and expertise. So we need people working on the hardware, making sure the robots are all like ready and whenever you need experiments to be done. And you also need people that are more on the engineering side. Like the
Mhm.
research and engineering are sometimes at odds with each other. Like
Right.
you can always have uh, you can shoot for having bigger and better models, but they conflict with the ideology of everything being onboard a robot
Mhm.
for inference. So robots have payload capacities and other limitations of networking and compute. So you can only have like a small amount of compute onboard any robot. So, and more so if the robot is like, think of a drone, you can only carry like really tiny onboard computers and they need to do much of the processing. So all of those mean you also need very strong engineering people to like take the best algorithms out there, but also design them, like compress them for low memory and low bandwidth compute. So yeah, the biggest learning is you need great teams to be able to do
Mhm.
like stellar work in robotics.
Of course. Right. That's a interesting conclusion there. Is there any like other technical issues that you would say are like or technical insights that you found throughout, you know, performing this project, like insights or, you know, novel shortcuts that maybe not shortcuts, but novel like different ways of approaching an issue that made the problem more realistic or more achievable?
Yeah, so the one key thing that made the project much easier for a group like ours compared to a lot of other groups which could potentially have had the idea at the same time. Like we put this project out a year ago, and I'm quite certain we are not the only people with
Right.
the idea at that point because large language models were a very popular phenomena. But what worked in our favor was like just uh, understanding the requirements and also the limits of what's possible on
Mhm.
robots. So that's what led us to just making the right choices, like not going for models that are more expensive because we knew there was no chance this could ever be deployed on the top of a robot. So, like, yeah, just talking to practitioners a lot is very helpful, and a lot of people in our team with themselves practitioners, like working at robotics companies in the past, like deploying software day in day out. So they would already tell us like a lot of things. Like you cannot have a runtime of more than 3 seconds for this particular algorithm, or
Right.
they would have other strong requirements, which would be like, well, this control loop, if it's running on a drone, this needs to run at 10 hertz. So all of those only come in when you have like people have deploy their software on robots and have this understanding of like how hard it is to actually get stuff done on a real robot. Yeah, so that's probably what gave us the most significant edge.
Right. So it's like a mix of having the experience and communicating and learning like of what the real boundaries are and working within those boundaries.
Yeah, and
Right.
those boundaries like keep changing every year. Like hardware tends to
Mhm,
get better,
mhm,
so they're not like as rigid. But when it comes to robots, it's always like that. Think of it as a hardware software co-design
mhm,
problem. So you can always make the problem like you can take the software you have and still be able to deploy it onto a robot platform by talking to the hardware team and asking them to like, well, design a robot that can carry like a few pounds more. Uh, but that may not always be feasible. So if you think about especially, well, you can always have robots that can carry more payload, but that would also reduce other things like battery time, and that could also have other ramifications. Like you need to figure out cooling solutions if your compute is going to overheat the robot. So it is it is like this dilly dally between do we handle this as a software problem versus do we think of this as a hardware problem?
mhm.
Like, do we fundamentally get different kinds of sensors that, you can always have sensors that are outside the visible spectrum, like think of radar
Yep.
and sonar. They make life easier, uh, but then they also require you to design your algorithms. Like you have really good vision models these days, but if you take this new modality, you might have to get data and like train
Train your
another
own. Yep.
model.
Mhm.
Yeah,
Right.
so it's always this. You need to find just the Pareto optimal solution that works best for your use case. And I don't think there is a solution that works well across all use cases.
Mhm.
So that's why it's like being a roboticist is always interesting and
Mhm.
challenging, regardless of whether you're doing a project for the first time or maybe the 100th time. There's
Right.
always something new to learn.
Right. And yeah, I think that's interesting. And then I did have one question, right? I never had the opportunity to look, very very in depth at your paper, right? But I saw you did touch on the NASA t-shirt recognition. So could you walk through maybe a different or maybe even the same example, but could you walk through like, a specific example or use case that really like highlights how representing the relationships of objects through like a graphical structure enables complex reasoning and planning capabilities, but like compared to the traditional like SLAM mapping techniques.
Yeah, that's a good point. So there is, since we put the concept graphs paper out, there's been like uh, a lot of other follow-up work, like people extending concept graphs to various kinds of scenarios. And one very common use case where like having relationships between objects is useful is when your environments start getting really, really large.
Mhm,
So imagine you need to create a map of like a city block,
mhm,
everything within the city block. So it just becomes unreasonably memory expensive if you start storing like everything in a flat hierarchy. So every
right.
single object inside every single apartment of every
Mhm,
building within that city block.
right.
You want something that's more hierarchical in terms of how it's organized. So one reasonable way of dividing up the city block could be like there's a city block and then there's multiple buildings on the city block. And within each building, there is like a floor, and within each floor, there's multiple apartments,
Mhm,
and within each apartment there's multiple rooms, and within each room there's like objects. So that is like a very concrete use case that a lot of people have already started exploring, like how do you store like map and store these large scale environments, because at a given point in time you only have to care about your immediate vicinity, and maybe you do care at some very abstract level of how the whole city block organization is. Like if you're planning out like if I plan my commute to office for tomorrow, I will not be thinking about like every single decision along the way.
Right.
I just be like, I'll take the subway, or I feel like biking. I might as well just bike tomorrow. There's
Right.
all these various modes that are very like far removed from concrete choices you'll be making. Like I won't be
Mhm.
planning it at a resolution of, well, I'll take 2 steps to my left and I'll pull the door open and I'll get out of the corridor.
Mhm.
So that'll come in much later. So having a graph structure with all of these relationships preserved helps maintain computational tractability in terms of planning.
Right, I can definitely see that because just having, like you said, that flat memory storage versus just like the general concept of that hierarchical just the hierarchy encodes information by itself, right? Just having it there
Yeah.
in the hierarchical format. Right. And then just one or two more questions to wrap it up, right? So uh one kind of like uh more big two kind of big picture questions, right? So what are some like key bottlenecks or challenges you see facing like the field of robotics and embodied systems in general?
Yeah. So, I mean, the nicest thing that is happening to robotics is also the most challenging aspect
Mhm.
we need to encounter for the next few years. Uh, the nice thing is that we have these more capable AI systems, and uh, we are beginning to use them more mainstream in robotics applications, and they've just enabled a whole new bunch of applications. Like you can now just talk to the robot and like give it tasks in language,
Mhm.
which I thought would just take many years for us to
Mhm.
solve.
Right.
But now we have these really capable systems. But with that comes the trade-off of, well, these systems are very capable, but also very compute intensive. So think of
Mhm.
robots that are actually like where you need everything to be self-contained on board. So most of these language models today are served via the internet to most
Mhm.
of us, and all of those models are like hosted on really large GPUs, and that's where like the moment you start trying to think of more condensed models for onboard use, you start losing out capabilities. So the
Mhm.
compressed models are not as good as the raw ones. And there's also this entire, the most performant models are also, they end up being proprietary. They're not released to the
Right.
public
Right.
as open source or open weights. So there's that aspect to overcome too. So yeah, the good thing to look up to how like modern AI is just taking over robotics, but the big questions are how do we keep up with these onboard inference requirements, especially for applications where you cannot assume you have reliable access to the internet.
Right. So like, well, yeah, so like lots of innovation is to be required to implement those larger models in terms of hardware and onboard computing power.
Yeah.
Right. And then one last thing, two more general questions. But right, so what are some open problems or future directions? Or like how do you see the field of robotics and AI like evolving within the next 10 years? And how are you like
Yeah.
excited to
So
explore it? Sorry, how are you like excited to explore it in like your research coming up?
yeah, I mean, the interfaces are where we'll see the most amount of work in the short term. Like, there's a lot of classical robotics techniques like SLAM for one, and there's also like lots of planning and control methods. And now with all of this explosion we see in AI, we're just figuring out ways to, and we're just scraping the surface here, making them more capable. So what we did in concept graphs was maybe like step zero or just step
Mhm.
one, but there's a lot more to be done. Like if we look at a lot of those experiments, they were done in static scenes. How do you just like handle this ever changing world? Like you have people moving around objects in your apartment, and how do you cope with all of that while like updating the maps in real time?
Right.
And uh, the kinds of work I am excited to like contribute to are again like yeah, what will the next generation of mapping systems even look like? All of that, but also there's a lot of new modalities that are not explored when we just talk about vision and language. There's like other modalities like tactile sensing, like touch
Mhm.
or robots that are severely underexplored. So there's lots of opportunities to contribute. Like how do you create a consistent representation of the environment that unifies as many modalities as possible?
Right. Yeah, like a bigger understanding of all the different senses makes it more humanistic and allows it to reason better. Right.
True.
And then one just final like question. So like, coming from the experience of a postdoc, right? What advice would you give for aspiring students, right? I'm in high school, but what advice would you give to aspiring students interested in pursuing a career, either academic or industry related in the fields of AI and robotics?
Yeah, so I guess the first step is to take robotics classes at
Hmm.
uh, like wherever you decide to go to school. Like uh, take a couple of robotic classes because robotics as a field is very, very wide,
Hmm.
and it is likely that like at this point, like even when I started out, I knew that I wanted to do robotics, but I was not sure what specific sub area of robotics I needed to pick, and that became clear only over time.
Right.
And it's also a consequence of some of the research groups I rotated with. So each group would offer me a different set of like skill building opportunities or research opportunities, and because of that, I end up developing expertise in like the subdomains,
Hmm.
and then I would specialize from there. So yeah, like first up, I'd say like just take classes, see what sticks. Like you might enjoy a few of these topics more than the others, and that's quite a natural thing. So not everyone would enjoy robot perception. There's always people that uh, more like uh, people just like designing robots for one, like designing new forms of
Right.
robot arms or whatnot, and that's perfectly fine. But yeah, it's like the sooner you are able to explore the space, like get a very quick sense of all the options out there, uh, then you can like start diving deep, and you can always switch around. Like robotics classes, at least the undergraduate level, they're designed to give you like a very broad exposure and idea of how robotics is as a field. It's very very broad, but then over time you will specialize like by course, like rotating for course projects or whatever that might look like.
Right.
Also, like there's internship opportunities you could be
Hmm.
looking out for. Yeah, so I'd say that that's the most natural way to be thinking about it. But also, just as you're doing right now, like reach out to other researchers or like people in companies doing robotics, and that'll help you give like gain like perspectives that are unique to each of those people.
Right. Well, thank you so much, Krishna, for all your time today. I really appreciated all your insight, and definitely different perspective on robotics and AI from what we see like during our club discussions.
All right, yeah, I'm glad we could finally chat.
Yeah, of course. Yeah, right.
Cool.
Thank you so
Okay.
much. Have a great day.
Yeah.
Bye-bye.